Hello and welcome to my YouTube channel ChemWis. In this video, we are going to discuss a very interesting topic, that is the Hammett equation. It has a lot of applications. It helps in understanding reaction mechanism, nature of substituents, QSAR in drug design, etc. I will try my best to keep this video short and to the point. We will cover the following points: basic understanding of Hammett equation, substituent constant sigma x and its physical significance, and reaction constant rho and its physical significance, where we will learn correlation between rho values and reaction mechanism for different reactions. So let's begin. The Hammett equation was developed by Louis Plack Hammett in 1937. It relates the rate constants for the basic hydrolysis of different meta and para-substituted ester of benzoic acid with the dissociation constants of different meta and para-substituted benzoic acid in water. The general structure of benzoic acid and meta and para-substituted benzoic acids can be drawn like this, where X is equal to H for benzoic acid and methyl, methoxy, chloro, bromo, nitro, etc. for meta and para-substituted benzoic acid. In water, it dissociates into carboxylate ion and hydronium ion. Let capital K be the dissociation constant. This is the general structure of ethyl benzoate and meta and para-substituted ethyl benzoates, where X is equal to H for ethyl benzoate and methyl, methoxy, chloro, bromo, nitro, etc. for meta and para-substituted ethyl benzoate. When it is allowed to hydrolyze under alkaline condition, it produces carboxylate ion and ethanol. Let small k be the rate constant for the hydrolysis. Electron donating groups make carboxylic group less acidic and decrease capital K or log of capital K, while electron withdrawing groups make carboxylic group more acidic and thus increase capital K or log of capital K. Electron donating groups make ethyl carboxylate group less reactive and decrease small k or log of small k, while electron withdrawing groups make ethyl carboxylate more reactive and thus increase small k or log of small k. So, if we plot rate constant for esters against the log of dissociation constant for different benzoic acids, we get a straight line with positive slope like this, where we can see that the values of log small k and log capital K are smaller when the ring is substituted with electron donating groups, while greater when the ring is substituted with electron withdrawing groups compared to the case when there is no substitution. We know that for a straight line, y is equal to mx plus c, where m is the slope and c is the intercept made by the line on y-axis. From the plot for a substituted benzoate ester and substituted benzoic acid, we can write log small kx is equal to rho log capital Kx plus c, equation number 1, where rho is the slope, also called reaction constant. For unsubstituted benzoate ester and unsubstituted benzoic acid, we can write log small kh is equal to rho log capital KH plus C, equation number 2. Subtracting equation 2 from equation 1 gives log small kx minus log small kh is equal to rho log capital Kx minus rho log capital KH. Or we can write log small kx upon small kh is equal to rho log capital Kx upon capital KH. Dissociation constant of benzoic acid in water, capital KH, and dissociation constant of different meta and para-substituted benzoic acid in water, capital KX, are known. So, for a particular substituent, log capital KX upon log capital KH is constant and can be replaced by sigma x called substituent constant. Now the equation will become log small kx upon log small kh is equal to rho sigma x. This is called the Hammett equation. Physical significance of substituent constant sigma x. It is a measure of overall electron withdrawing or electron donating effect exerted by substituent X on the reaction center. It varies from -1 to +1. By definition, for x is equal to h, sigma x is equal to 0. Negative sign indicates electron donating nature while positive sign electron withdrawing. Its magnitude indicates the extent of electron withdrawing or electron donating effect exerted by X on the reaction center. Its value remains constant for a particular substituent in a specific position irrespective of nature of a particular reaction. Let's have a table showing values of substituent constants for different substituents at meta and para positions. First, look at the values for meta substituents. We can see that meta-2-butyl and meta-methyl have small negative values, suggesting that they are weak electron donor in nature. By definition, value is 0 for H. Methoxy and hydroxy have small positive values, suggesting weak electron withdrawing nature at meta position. The moderate positive values for fluoro, chloro, acetyl and bromo suggest that their nature is moderate electron withdrawing at meta position. Higher positive values for nitrile and nitro suggest a strong electron withdrawing nature at meta position. Let's compare the rate of alkaline hydrolysis of metanitro and metamethyl ethyl benzoate with that of unsubstituted ester, that is ethyl benzoate. We can draw the general structure of ester like as, where X is equal to H, methyl or nitro. The rate limiting step is the attack by hydroxide ion on carbonyl to produce negatively charged transition state, which collapses to tetrahedral anionic intermediate. Thus, electron withdrawing nitro group will stabilize the transition state and enhance the rate of hydrolysis, while electron donating methyl group will destabilize the transition state and decrease the rate of hydrolysis. In real case scenario, Metanitroethyl benzoate with plus 0.71 sigma x value for metanitro group hydrolyzes 63.5 times as fast as unsubstituted ester, while metamethyl ester with minus 0.07 sigma x value for metamethyl hydrolyzes 0.66 times as fast as unsubstituted ester. Now look at the sigma x values for the para-substituents. It is evident that for a particular substituent there is not only change in the magnitude but also sign. For example, both the methoxy and hydroxy groups have sigma x values of plus 0.12 at meta, but at para, these values are minus 0.27 and minus 0.37, suggesting that these groups are acting as electron acceptors at meta and electron donors at para. This is because at para there are two effects operating in opposite directions: inductive effect by which they withdraw electrons and mesomeric effect by which they donate electrons. Mesomeric effect dominates over inductive effect. Therefore, overall they behave as electron donors. This is the reason why the rate of alkaline hydrolysis of 4-hydroxy and 4-methoxy esters is less than the rate of alkaline hydrolysis of unsubstituted ester. Physical significance of reaction constant Rho. It is a measure of susceptibility of a reaction to the electron donating or electron withdrawing effect exerted by a substituent X. It may be positive or negative. Aqueous dissociation of meta and para-substituted benzoic acid is the standard reaction, for which by definition Rho is equal to plus 1. A positive Rho value suggests more electron density in the transition state at the reaction center than in the starting material. That is, electrons flow away from the aromatic ring in the rate determining step, while a negative Rho value suggests less electron density in the transition state at the reaction center than in the starting material. That is, electrons flow towards the aromatic ring in the rate determining step. Now we will learn how to find Rho value of a reaction. For this, let's revisit the Hammett equation. Log small kx upon small kh is equal to rho sigma x. For comparison, write the straight line equation y is equal to mx plus c. In the Hammett equation, c is equal to 0. So, if we plot log small kx upon small kh against sigma x, it will result a straight line passing through the point of intersection between x and y axis. Sigma x values are known as dissociation constant in water for benzoic acid, and different meta and para-substituted benzoic acids are known. To determine the Rho value, determine the rate constant small kh and rate constant small kx at least for 3 substituted esters. Plotting 3 different log kx upon kh against 3 sigma x will give 3 different points. Now draw a line passing through these points. The slope of this line is equal to tan theta, and that will be equal to rho. Before we move ahead, let's have a summary for interpreting the Hammett Rho values. Rho values between -1 to +1 come under the category of small rho values. This is the case when aromatic ring is too far away from the reaction center. There is no change in the electron density of aromatic ring, or the two rho values cancel out each other. Rho values between +2 to +4 come under the category of moderate positive rho values. This is the case when negative charge is generated near the ring. Electrons flow into the ring in the transition state. Rho value +5, +6 and higher come under the category of large positive rho values. This is the case when negative charge is generated on the ring or delocalized around the ring. Rho values between -2 to -4 come under the category of moderate negative rho values. This is the case when positive charge is generated near the ring in transition state. Electrons flow away from the ring. Rho value -5, -6 or higher magnitude come under the category of large negative rho values. This is the case when positive charge is generated on the ring or positive charge is delocalized around the ring. Now we will go through examples where we will use the rho values for the interpretation. Let's first have equilibria with positive rho values. We are going to take the example of aqueous ionization of carboxylic acids to study the effect of movement of carboxylic acid away from the ring on rho values. These are four sets of equilibria corresponding rho values. By definition, it is +1 for the first one. For second, third and fourth, it is +0.5, +0.2 and +0.5 respectively. We can see that the rho value decreases as the carboxylic acid moves away from the ring, suggesting that the susceptibility for the ionization of carboxylic acid to the polar effect of substituent on the ring decreases as the carboxylic acid group moves away from the ring. In the fourth reaction, the rho value increases again as CC double bond is better transmitter of electronic effect than CC single bond. For this ionization, the rho value is positive because there is generation of negative charge in the transition state. The magnitude is small as the negative charge is not able to delocalize into the ring. Let's take the example of aqueous ionization of phenol. In this case, the rho value is +2.3. Here, rho value is positive as there is generation of negative charge. The magnitude is moderate as the negative charge can delocalize around the ring. In the case of aqueous ionization of anilinium ion, the rho value is +3.2. The sign is positive as there is increase in electron density on nitrogen, and the magnitude is moderate as the lone pair is delocalized around the ring. Now we will discuss few reactions with positive rho values. We are going to take the example of SNAR reaction between substituted 2-bromo-nitrobenzene and piperidine to produce piperidine substituted nitrobenzene. Here, there is attack by nucleophilic piperidine in the rate determining step to produce anionic intermediate that has negative charge on the ring. Here, the negative charge is delocalized around the ring and also on nitro group. The rho value for this reaction is +4.9. In this case, we are not getting full value of rho because nitro group is also helping in negative charge delocalization. In the final step, there is removal of bromide ion to produce product. Let's take the example of addition-elimination reaction involving 2 butoxide and 1-bromo 2,2-diaryl ethene. In this reaction, in the rate determining step, butoxide ion adds to the alkene to produce carbon ion having negative charge on benzylic carbon. Here, there is no nitro group for the delocalization of negative charge. It is mainly delocalized round the ring. In the second step, there is elimination of bromide ion to produce substituted product. The Rho value for this reaction is plus 9.0. This is because there is generation of negative charge in the rate determining step, which is mainly delocalized round the ring. Reactions with negative Rho values. The first example which we are going to discuss is SN2 reaction involving phenoxide ion and ethyl iodide. Here, oxide ion attacks from the back side of iodo to produce negatively charged transition state, which then collapses into product. Since there is flow of electrons away from the ring, so despite having negative charge and transition state, the Rho value for this reaction is negative. It is minus 1.0. Let's take the example of SN1 reaction involving tertiary benzyl chloride and water. Here, in the rate determining step, removal of chloride ion gives tertiary benzyl carbocation, which is then attacked by water molecule to produce alcohol. The Rho value for this reaction is minus 4.5. The reason for negative sign is that there is generation of positive charge on the reaction center in rate determining step and electron flow is away from the ring. The reason for high magnitude is that the positive charge is generated on the carbon next to the ring, which is delocalized round the ring. Now we are going to take the example of electrophilic aromatic substitution reaction. In a general electrophilic aromatic substitution reaction, there is an aromatic ring and an electrophile. The electrophilic attack gives a cationic intermediate in the rate determining step. The cationic intermediate is stabilized by resonance. In the second step, there is removal of proton to produce substituted product. The Rho value for these reactions range from minus 5 to minus 9. The reason for the negative sign is that there is flow of electrons out of the ring, and the reason for the high magnitude is that the ring electrons are used, leaving a positive charge on the ring itself in the rate determining step. If we take the example of nitration reaction, the Rho value is minus 6.4. The next example which we are going to discuss is Diels-Alder reaction, in which a diene and a dienophile undergo 4+2 cycloaddition reaction in concerted manner to produce adduct. The Rho value for this reaction is minus 0.6. The small value of Rho is consistent with the mechanism not involving charge accumulation or disappearance in the transition state. Negative value supports the fact that the Diels-Alder reaction is somewhat faster with aryl ring having electron donating group. Another example is acylation of anilines with benzoyl chloride. In this reaction, attack of lone pair of amine on carbonyl in rate determining step gives tetrahedral intermediate that has positive charge on nitrogen. In subsequent step, there is removal of HCl to produce amide. The Rho value for this reaction is minus 2.69. The negative sign of Rho is because there is electron flow out of the ring for the stabilization of transition state. The magnitude is moderate as there is positive charge on the atom adjacent to the ring. Next example is electrophilic addition of bromine to styrene. There are two possible mechanisms. First mechanism involves attack of alkenic pi bond on bromine to produce cyclic bromonium ion in the rate determining step, and then attack of bromide ion on bromonium ion to produce product. Second mechanism involves attack of alkenic pi bond on bromine to produce benzylic carbocation in the rate determining step, then attack of bromide ion on carbocation to produce product. Rho value for this reaction is found to be minus 5.7. This is consistent with the formation of benzyl cation in the rate determining step, which is delocalized, where the charge is delocalized around the ring. So, the mechanism involving benzyl cation intermediate is the correct mechanism. The last example which we are going to discuss is also related to electrophilic addition reaction of styrene. In this example, there is addition of phenyl sulfonyl chloride. Similar to the previous example, there are two possible mechanisms. First involve attack by alkenic pi bond on the sulfur of phenyl sulfonyl chloride to produce three-membered ring cationic intermediate, which is then attacked by chloride ion in the next step to produce product. In the second mechanism, attack a pi bond on sulfur of phenyl sulfonyl chloride keeps benzyl carbocation, which after attack by the chloride ion keeps product. Rho value for this reaction was found to be minus 2.7, which is consistent with the formation of three-membered cyclic cationic intermediate. So, in this case, the first mechanism is the correct mechanism. That's all in this video. Please subscribe my channel and press the bell icon if you like this video. Thank you very much for watching this video.